My guest today is Professor Andrew Jaffe, who's Professor of Astrophysics and Cosmology at Imperial College, London. He's the director of the Imperial Centre for Inference and Cosmology. He studies the history and evolution of the universe as a whole. Welcome, Andrew.
Hi, Gill. It's great to be here.
Yeah, thanks for doing this. So you have a book very recently, maybe last year, The Random Universe, How Models and Probability Help Us Make Sense of the Cosmos. So let me start at a very high level. Is the universe truly random? And secondarily, have we made sense of it?
Wow, that's a big question. The universe isn't totally random, although it really
Yeah.
depends on what you mean by totally and what you mean by random. But
Yes.
it's random in the sense that there are bits that are not explicitly predicted by our theories,
Yeah.
but it's not totally random because our theories do make some very strong predictions
Yeah.
about how different parts of the universe relate to each other. They tell us what the different constituents of the universe are,
Yeah.
and we think so. They tell us that there are protons and neutrons and electrons and photons, and we think that we have theories, or we have theories. We don't know if they're exactly the right theories that
Yeah.
tell us also about how those different components of the universe are arranged in patterns around the universe. So it's not completely random in the sense that everything is just completely smooth and there's just tiny small fluctuations on top of them. The
Yeah.
fluctuations that we do see, the difference from being completely boring and uniform,
Yeah.
the statistical properties of those are predicted by our theories.
Yeah. So I'm fond of saying, Andrew, that God has a sense of humor. If it were totally predictable, we don't really have a reason to exist because everything is sort of known. And so she has made some probabilistic adjustments to the system, it looks like. And she's not, it looks like she's not going to allow us to really understand it because it's quite difficult. It's very complex and nonlinear system. And so let me go into the sort of the second part of your book. I'm trying to get to that. So before that, in the first part, you talk about physicists and philosophers, which I often found very interesting. Um, is physics and philosophy sort of aligned? Are those two disciplines important for us to think about?
Well, I think they're both very important for us to think about. Certainly,
Yeah.
historically, they were very closely aligned, right? They're really
Yeah.
physics was a certain branch of philosophy, natural philosophy, until
Yeah.
until the 19th century. It really only differentiated itself and called itself physics then.
Yeah.
But yeah, I mean, I think we, those of us who really want to understand the universe, need a little bit of both. I think a little bit
Yeah.
of proper numerical science as well as philosophy, because uh, all that our science can do is sort of describe things, and
Yeah.
the philosophy can help us situate that mathematical, because usually it ends up being mathematical nowadays, that mathematical description
Yeah.
into a larger, use a big word here, epistemological framework, which is sort of about how we know things. And maybe that's even about a larger, another big word,
Larger,
ontological framework
larger
about how things
context,
really are.
maybe.
Sorry?
Context,
Yeah,
context in
so,
some ways. Yeah. Yeah.
excuse me. Yes, yeah, it's all, we could just give you the mathematical laws and say this is the way things are, but
Yeah.
we know that the process of science is always sort of a process and it's always tentative. So
Yeah.
it's hard for us to be sure that it's really the way that things are, but we
Yeah.
are sure at any given time that our theories are a pretty good description, at least, of what's
Hmm.
going on, and that the philosophical drive helps us, uh, yeah, as you say, give it context, put it together with other
Yeah.
things that we know.
Yeah, it's really interesting. I mean, so I was an engineer and an economist, Andrew. So I thought, everything's described by equations. Even in economics, we think that, which there's no basis for it. Actually, we haven't found anything. Um, and so, and I'm increasingly moving toward yeah, I mean, you have to put all this information in context. We have this artificial intelligence thing going on,
Hmm.
which I don't really have really understand actually. And so let me get into the second part of this book, more about physics. So entropy and information. This is a very important topic in physics nowadays. Um, and Hawking radiation sort of put some things in context for things that we don't quite understand. So you say here we need mathematics of probability because so much of the world around us seems random. We can predict what's going to happen, and we want to assign probabilities to the different possible outcomes. Um, so when I read some stuff, some things coming out in quantum mechanics and other subjects, it almost like everything is probabilistic, isn't it? I mean, we don't really have a deterministic. That guy Newton put everything in very clear terms. F equal to ma is very easily understood,
Hmm.
and then after that, everything seemed to have gone downhill in some ways. What do you think? Yeah,
Well, right. So it looks like at the very bottom, there's an important
yeah,
sense in which the world isn't deterministic. There are physical laws, we think, but
yeah.
those physical laws don't say what's going to happen. They give kind of a list of the things that might happen, and then it tells us how likely, how probable the different possible things are. Now, not everything is possible, so there are senses in which it really is curtailing
Yeah.
the picture of the universe that we might have. And some things are much more likely than others. The reason why Newton did so well is that despite things having this, and I'm not sure even we've used the word yet, but quantum mechanical underpinning, which is where
Mm.
these probabilities seem to bubble up from, despite that, when you get large numbers of particles together in large amounts of mass, where large doesn't mean like the size of a planet, it just
Yeah.
means anything that we interact with that we can touch and feel and use.
Yeah.
Once you have that much mass, then for much of the kinds of predictions we want to make, the probabilities of quantum mechanics are incredibly sharp. And they're just telling us,
Mm.
well, in fact, F equals ma is a perfectly good rule when you're throwing a tennis ball, or
Yes.
indeed when you're looking at how something as light as a feather or even a gnat, behaves, as long as
Or
it's
even
careful
going to
about
the moon. Even going to the moon,
spe-
it works.
going to
Yeah.
the moon like in 1969, or indeed like they're
Yes.
about to do a few
Yeah.
days after we record this podcast. We hope. Yeah. So all
Yeah.
those things, you don't need quantum mechanics to make those predictions about how to use a rocket in that sense, but you do need it once you start to get into the realm of the small. And it's not to say
Yeah.
that it doesn't matter on those large scales. It's just that, or that it doesn't apply on those large scales. It's just that the predictions, all the probabilities are indistinguishable from one as far as we're concerned, from being absolutely likely.
Yeah. So we deal with, as humans, we deal with this all the time. So we know that, if you throw a dice with six faces, you have equal probabilities. Well, if the dice is proper, equal probabilities of coming up with 1 to 6. So you say here the kinds of randomness. I mean, this is sort of a conceptual issue, which is so. Suppose I throw two dice and add them up. Now I have a sort of a probabilistic distribution that I can bank on, right?
Hmm. Yeah, so seven is most likely, right? As you
Yeah,
know, if anyone who's ever played craps or even Monopoly,
yeah,
knows that when you throw two dice, then that, because you can make it 6 and 1 and 1 and 6 and 2 and 5 and 5 and 2 and 3 and 4 and 4 and 3. You can make seven more ways out of two dice than anything else, and so it comes up most often. It's just that simple. Whereas one dice each, there's only one way to make each of 1, 2, 3, 4, 5, and 6, and so
yeah,
that makes it even.
yeah. So entropy. So one of the chapters you have here is entropy and matter. Entropy has been a very puzzling concept for ordinary people like me. Um, So you say the concept of entropy did not originate with Shannon and his efforts to understand the mathematics of communication. Rather, in the middle of the 19th century, physicists tried to come up with a modern theory of heat superseding the old idea. that it was a substance. Talk a little bit about that. Yeah.
So, right. So entropy started out as sort of a old-fashioned phenomenon, as it were,
Yeah.
when it was realized that when you tried to extract useful work from a system, there was always some amount that you couldn't get to, some amount
Yeah.
of energy that was in the system that was just lost to you. As you know, if you wanted to make a steam engine and things like that, which is what people were trying to do at the time. All of
Yeah.
this, all of this original stuff was exactly an engineering problem. They were trying to understand how you make engines as efficient as possible.
Yeah.
And they came up with this idea of entropy, which was a
Yeah.
description of the energy that was not accessible to you as an engineer.
Okay.
And that was the original conception. And then in the mid 19th century, in the mid 1800s, people like Gibbs and Boltzmann um, uh, realized that you could describe what's going on under the hood
Hmm.
if we took that our model of matter was that it was made up of tiny moving parts,
Hmm.
atoms and molecules, as we call them
With,
now,
with different temperatures, some
with
ways,
different
right?
temperatures. That's right. They can
Yeah.
have different temperatures, and
Yeah.
to a good approximation, all you need to know about the kinds of things that make up matter when you're talking about this sort of stuff, about how to extract work from it, is
Yeah.
the mass of the particles that make it up, something about the possibility that they can spin or vibrate, excuse me, and then the
Yeah.
temperature of the system. And that's all there is. But what they further realized was that when once you had that temperature, that
Hmm.
actually gave you probabilities. That told you the probability
Hmm.
of the speed that a given particle might be moving. Now, because there's
Yeah.
trillions and trillions of such particles in the reservoir of gas that's being used in this engine, let's say,
Hmm.
then you end up getting this bell-shaped curve
Yeah.
that describes the velocities of these particles very, very, very well indeed.
Hmm.
But it really is a probability distribution. And by counting up the possible states of the system, that essentially gives you a description of the entropy.
Okay.
And then,
Yeah.
and that, and that was sort of it was not an expected result that this thing that had been originally invented to describe the waste heat in when you're
Yeah.
building engines
Yeah.
happened to be described by something about the probabilities of states that make up the
Hmm.
particles in the system can
Yeah.
take, and that was not expected. And it was sort of this amazing insight of people like Gibbs and Boltzmann that I mentioned,
Yeah.
that you would get out this formula that described one thing by thinking about it in this very different terms that weren't even around
Yeah.
when people like Clausius, who invented these entropies, originally were putting them together.
So I don't know the history, Andrew. So is it one of those situations where practice instructs theory or instructed theory?
Oh, absolutely. I mean, the whole
Yeah.
history of all of science really is we mostly have these puzzles in the real world
Hmm.
practice that we try to understand with our theories. And sometimes we get lucky and we end up with a theory that sort of predicts things that we have yet to observe.
Yeah.
And sometimes we get very lucky and we have, somebody just comes up with a theory that really doesn't explain that much new at the time, but just
Yeah.
happens to fit the data that are going to come in a few years. But most likely, most often, the reason why Einstein came up with his theory was twofold. One was because it was a beautiful extension of trying to understand some other theoretical ideas that were going on, but it was
Yeah.
also trying to understand experimental results
Yeah.
that were out there. So science proceeds neither by pure uh, ratiocination, right? Pure thought, nor by
And
pure experimental results, just giving us a list of all the things that happened in the world.
so in the middle, there are thought experiments. Einstein was a great guy on thought experiments.
Mm-hmm.
So I want to go another chapter. So quantum randomness,
Mm-hmm.
um, like a deer in the headlights. When I hear quantum mechanics, I know nothing about it. It seems very, very weird. So you say here the so-called classical physics of Isaac Newton's mechanics, James Clerk Maxwell's electromagnetism, and Albert Einstein's gravity make specific predictions. If you give me enough information about the locations of the heavenly bodies, I can predict their future paths. Um, so that's about gravity. Um, so these things don't play well together in some ways, right? So Einstein's gravity works in very large scales. Um, we know the electromagnetism really sort of propagated by photons work a little differently. And then we know all about the classical physics. So, and then we got this quantum mechanics thing. I have no clue about this, Andrew. So where are we now? Are we understanding this better, or are we going into some sort of black hole, so to speak?
Well, yes and no. I mean, for or both of those things, I suppose.
Yeah,
So, in fact, you already hinted that we have cracked a lot of the problem because when you said that
yeah,
Maxwell's electromagnetism is carried by photons, that so Maxwell's electromagnetism was a classical field theory, we call it. So it
yeah,
describes this electromagnetic field that pervades the universe. That's the thing that travels down your wires when you have electricity. It's the
yeah,
excuse me. It's what makes the light happen in your lamp. All the things that have to do with electricity and light and magnetism.
yeah,
Those many of them can often be described as very classical phenomena in that sense. But
yeah,
when you look very closely at them, we see that they are actually perfectly well described by the theories of quantum mechanics. And quantum mechanics
mm,
is, as we talked about before, this weirdly probabilistic theory that
yeah,
talks about how often things happen as opposed to what's
yeah,
going to happen, right? And even electromagnetism um, satisfies that. It is at bottom a quantum mechanical theory called quantum
yeah,
electrodynamics,
mm,
QED,
yeah,
sort of is the term of art there, and it works. It is an amazingly good description
mm,
of how light and electricity and magnetism work at a very basic level. And that doesn't mean it's just about the light itself, because it's about how
mm,
light and the electromagnetic field is formed. So it happens when to be part of that, you also need the quantum mechanical theory of particles like electrons and protons, because
yeah,
those charged particles that make up the atoms that we're made out of, that's
right,
how electricity gets generated. That's how electromagnetism gets generated.
mm,
So the theory of quantum electrodynamics talks about how those charged particles work and how when they move around, essentially, they
yeah,
produce and interact with light. And that is a great quantum mechanical theory that when
yeah,
you zoom out into large physical scales works just like Maxwell's theory of electrodynamics, which was a so-called classical theory. So that's a really good example of
yeah,
how a lot of the time the classical mechanics and the quantum mechanics work perfectly well together. Right? There's no
yeah,
there's no controversy
yeah.
about that whatsoever. The
No
problem, as
controversy.
you
Yeah,
alluded to, I
yeah,
mean, there might be controversies in understanding the again, to use this word again from before, ontology of quantum
yeah,
mechanics, of
yeah,
what the real things that are in the world, if we can only make probabilistic descriptions of them, what that means. But
yeah,
there's something I talk about in the book, which is the rule that a lot of people have for how to use quantum mechanics and how to understand it is shut up and calculate, which means that
yes.
we
The
don't really understand.
Copenhagen interpretation of quantum mechanics.
Yeah.
Yeah,
So we don't
yes,
really understand all of what it means
yeah,
in some deep, deep, deep sense, but we know absolutely enough that there is no situation that we've encountered yet in which we don't know how to use it.
mm.
Right. So it's
It,
this
it,
so
it seems. Yeah, I mean,
hmm,
it seems like gravity is the bad kid
yeah,
in the
exactly. So
school.
that is the one situation in
Yeah,
which
yeah,
we think that our understanding of quantum mechanics is inadequate to the task. So we
And
don't yet have.
everything else, if I understand you correctly, Andrew, everything else quantum mechanics could have reasonable explanations how things work. Gravity is still sort of out there. Um, this is not in your research, but I just want to get your idea on this. So um, there have been a lot of so there's string theory, 10 or 11 dimensions. There have been some other ideas that said, put one more dimension that we cannot access on the 3+1 thing that we have currently, and then gravity is explained. So where are we on this multi-dimensional hypothesis?
Well, that's a very good question. Yeah. So there are lots of ideas for making theories that either succeed or go some way towards succeeding in marrying the ideas of quantum mechanics and the ideas of gravity.
Yeah,
And as you alluded to, one of them is this fairly long-standing idea called string theory,
yeah,
where the fundamental constituents of the universe are described exactly by quantum mechanics,
yeah.
as we talked about, but instead of being point-like particles, little
Mm,
dots that have no extent, they are they are little strings. They have length but nothing else.
yeah,
And it turns out, and as you said a minute ago, this is not my bailiwick, but I'll do my best. It
yeah,
turns out that you can only write down a self-consistent theory which has these string constituents
yeah.
in 10 or 11 spatial dimensions.
Okay.
Okay.
Yeah.
Now you may have, last time any of us looked around, we didn't live in 10 or 11 dimensions. We lived in three.
We don't
And
know yet.
so,
We don't know yet, I would say.
well,
Yeah.
right. So we live in at least we
Yeah.
live in three so-called large
Yeah.
dimensions.
Yeah.
So,
Yeah.
so what may be possible is that we actually the universe writ large, does have more than three dimensions,
Yeah.
but the other seven or eight, six or seven, whatever the right numbering is, I can't
Yeah.
do arithmetic in my head. The extra number of dimensions
Yeah.
is somehow inaccessible to us, and there's sort of two ways that can manifest itself.
Yeah.
One of which is the other dimension is in some sense small.
Yeah.
So, imagine instead of a three-dimensional world, imagine a two-dimensional world. So like
Yeah.
a sheet of paper or something like that. But that, you're a creature that lives in the two dimensions, in the flatland of the two dimensions.
Right.
The whole thing is in three dimensions, but somehow you're confined to being within, a centimeter of the surface,
And you will never
right?
see the third dimension because you
And
you can't access it in some ways. Yeah.
yeah, so you're confined,
Yeah.
within a centimeter or a micrometer, but you
Yeah.
are, you are 5 feet big, so you don't
Unless
even
unless
notice
there
this
is a
other.
unless there's a jumping ant said, "Hey, I just
Yeah,
jumped," and then there's something else out there. Yeah.
but you're not, but all your muscles only work in the two dimensions, right? They don't even work in the other dimension. They're not pushing in that way,
Yes.
so you
Yeah.
don't even notice it. So that's one possibility. The other is that it sort of loops around in that dimension.
Yeah.
It's kind of like a video game where you leave one side and you come in the other, but it's a tiny, tiny amount. So also
Yeah.
you don't notice it then. Um, The other is that you're like just literally confined, but there is a big third dimension. You just
Yeah.
don't. You just the physics kind of keeps you, unless you are very very energetic, keeps you attached to this membrane, or sometimes just called a
Yeah. Yeah.
brain, but spelled
Right. So
BRANE.
you cannot go any further. Yeah.
Yeah.
So I think my hypothesis is that God has a sense of humor. I think works out actually. She's doing all the stuff to keep the simulation going in some ways. Um, so you have another chapter. So the quantization. So I want to get into a little bit about quantum mechanics. So because Schrodinger's equation, you say here for an
Mhm.
electron in an atom, only makes sense. It only has solutions for specific values of electrons' energy.
Mhm.
So talk a little bit about Schrodinger's equation. I mean, this has fundamentally changed our understanding of how things work, right?
Yeah. So about 110 years ago, 120 years
Yeah,
ago, um, Schrodinger, sort of on the back of lots of other work that was being done at the time, wrote down this equation that described, and at the time he didn't really know what it described, but it described
yeah,
something about systems, and in particular the system that people were really exercised about were atoms. We're trying to
Yeah.
understand the possible ways that an atom could emit light. And again, this is back to that link between charged particles and light.
Yeah.
And we know again from observations that atoms can emit light and absorb light only at very
Yeah.
specific energies.
Okay.
And we tried to understand how that could be. And Schrodinger was able to write down an equation, and he showed that this quantity that the equation described, which we now
Yeah.
call the wave function, only when you apply the things we do know about the hydrogen atom,
Hmm.
only allows solutions with certain values of this thing that we realized was the energy of the electron. And
Oh, I
those
see.
energies
Yeah.
corresponded, when you put in the formula, corresponded exactly to the observed so-called lines of a hydrogen spectrum, which you can
Yeah.
see in the sun. You can see by basically burning hydrogen, which is dangerous, but you can do it carefully, and by looking at the light that comes off of it with a spectrograph or a spectrometer, and you see
Yeah.
that it only has these very, very specific
So it's sort of
lines.
quantized.
Yeah, it is
It's
exactly
yeah.
quantized.
Okay.
Yes, this
Yeah.
is where the word comes from, and and what wasn't what wasn't understood immediately is what else that wave function described. So we saw that
Hmm.
it only had solutions at particular values of the energy, but then it was realized that if you took that function and you squared it, so you
Hmm.
just took it and multiplied it by itself essentially,
Hmm.
it described the possible locations, the probabilities of the
The
possible
probabilities.
locations
Okay. Yeah.
for an electron orbiting a proton. So
Hmm.
you might have a picture in your head that that an atom is kind of like the solar system, with the sun at the center
Yes.
is like the
Eh,
proton, and then there's like planets
That's
going
that's what we
around with
have been
different
taught
orbits. Yeah,
incorrectly, I would imagine.
and
Yeah.
that's not a particularly good picture because
Yeah.
they don't really orbit in a circle or even an ellipse around it.
Yeah.
Once you have a particular energy, where you are is you're somewhere in this cloud that's
Yeah.
around the atom, and if you go and look for it, you'll find it with a probability given by that function. But
Yeah.
until you go look for it, there's no way that it makes sense to even think about it kind of going around in an ellipse or in a circle. It's just in that cloud somewhere, and then you can go and look for it and find out where it actually is when you looked.
Mm. Okay.
So it's a bunch
So
of
I want to go
clouds of
into
things.
cloud. It's basically a probability distribution
Exactly.
around the nucleus. So I want to go into something sort of related, but so Wigner's friend and
Hmm.
Schrodinger's cat.
Yep.
Um, Schrodinger's daughter, I think I read something. She said my dad didn't like cats. That's why he did this. I don't know if that's true or not. So, but it's a larger question. Wigner's friend. So there has been a lot about the Bell ideas and Bell
Hmm.
theorem, and so talk a little bit about. I mean, this is sort of recent, isn't it? I mean, um, we have been doing experiments that could prove something that we thought was really insane.
Yeah, that's one way of putting it. So right. So this is bundling up a whole bunch of things, but
Yeah,
so the question is, if quantum mechanics is only about probabilities, what does that mean for what's really happening, right?
yeah,
So because in this Copenhagen interpretation that you mentioned before, what we're taught in quantum mechanics lectures when you're in the first or second year of university,
yeah.
and indeed what I have taught when I've taught those classes, is that what happens is you have this wave function that I mentioned that describes your system, whatever it is, whether it's a
Yeah,
cat or an electron, and then in some real sense, the the cat or the electron doesn't have the thing that you're trying to measure, doesn't have that property until you look.
yeah.
Okay, so that's called the collapse of the wave function,
Right.
and we can kind of
Very,
live with
very
that.
inelegant, I have to add. That
Very
doesn't
inelegant.
make any sense. Yeah.
It's inelegant because it seems to
Yeah.
privilege our active measurement as something that
Yeah.
you have to kind of explain within the theory,
Yeah.
and that doesn't make a lot of sense. And it sort of, and when you're writing down the theory, it sort of says there's this split in the universe,
Yeah.
which is between the quantum mechanical system that you're measuring and then the rest of the world.
Yeah.
And can you have that make sense? And
Right.
in a naive way, there's certainly no way to have that make a lot of sense. The whole world should be describable by the same ideas, and so how do we make that work? And it really, it doesn't seem particularly problematic when you're talking about an electron, but if you're talking about a cat or your
Yeah.
friend, then it is more weird. And so let's talk about Wigner's friend
Yes.
first. So probably
Yeah. Yeah.
listeners may have heard of
Yeah.
the poor cat, but Wigner's
Yeah.
friend, nothing bad happens to the friend. Don't worry. Uh, Instead, imagine that you have your friend. She's a scientist in her laboratory, and
Yeah.
she is performing some experiment, some quantum mechanical experiment on an electron or something like that. And she's deciding whether the electron is in, the lowest energy state of this hydrogen atom or some other state, let's say.
Yeah.
And and until she makes her measurement, then according to this standard interpretation or way of describing quantum mechanics, then it doesn't really have an answer. Okay, whether
Doesn't
what's
have an
happening. But
answer. Yeah. Yeah.
imagine that you are, you instead consider your friend and her laboratory. That's
Yeah.
your experiment, right? You put her
Yeah.
in a really well-sealed laboratory and you say, "Hey, go do an experiment, and tell me in a week or tomorrow or whenever, or
Yeah.
in 2 hours, maybe she wants lunch. Um, tell me what the outcome was. Tell me
Mm.
whether it was in the first state or the second state, right?" And as far as you're concerned, this is an enormous quantum mechanics experiment
Yeah.
where instead of looking, she has to look at some dial on some apparatus to tell her whether it was the energy of state one, or level one or some other energy level. But
Yeah.
the way you're going to find out the outcome of this experiment is she's going to tell you. Right? She's just
Yeah.
going to open the door and say, "Hey, Vigner, two," right?
Yes.
Um, and
Yeah.
and that to you, that is the moment of measurement. And so the question is, what's
Yeah.
happening as far as your quantum mechanical description of her laboratory is concerned?
Yeah.
That
Yeah.
whole laboratory is in this giant wave function, which may be
Yeah.
really hard to write down mathematically. But until
Right.
you find out if in this very standard interpretation of quantum mechanics, then
It
nothing
collapses.
collapses until she tells you this thing,
Yeah.
or
Yeah.
until you ask
Okay.
her this thing, which is weird,
Yeah.
right? As far because
Right.
you're pretty sure, because you're a human and understand something about other humans and psychology, that
Yes.
before she opened the door to tell you, something else was happening in that room, and she was having an
Yeah.
experience of what was happening. It wasn't that there were two of her, and
Yeah.
or there was a multiplicity of hers who were sort of intermingled with each other, and they were all happening. No, as far as
Mm.
those were both happening. But that doesn't seem to be the mathematics of quantum
Yeah.
mechanics leads you to something that isn't a description of that happening. And that
Right.
seems to be, if not an actual contradiction,
Mm.
at least some tension in our understanding of the theory is there. And you
Yeah.
can,
Lot of tension. Yes. So
yeah.
I want to talk about many worlds.
Hmm.
And I think I've proven this, Andrew. As you know, after the last election in the US, we are living in two worlds, actually.
Yep.
330 million people, they don't seem to know the other world that others are living in. So we have sort of practically proven this, the many worlds hypothesis. So you say here the most famous way of looking at quantum mechanics, one that has found its way into popular culture from comic books to movies, sliding doors and everything everywhere all at once, is the many worlds interpretation, first discussed by Hugh Everett in the late 1950s. I was never a fan of this, Andrew. So set me right here. So this cannot be tested. It seems to me it is a little bit of a sort of ideas that you put out there as a possible mathematical construct. But if you cannot test it, it's not that useful, is it?
Well, so the problem with interpreting quantum mechanics
Yeah,
is that many of the interpretations are engineered to agree with the mathematics that we already have. And
yeah,
so by construction, they're gonna not be testable in the sense that they're all gonna just agree
um,
with the formalism that we already have.
yeah.
So the Copenhagen interpretation just gives the same the same predictions as the many
Mm.
worlds hypothesis.
Many
It just
words. Yeah,
does. It's so there
yeah,
isn't a way to, as far as we know, So scientists are clever, so don't count out the possibility that what I say is incorrect. So,
Yeah.
in I think what you have to do is look for a sort of a bit of the theory that eventually jumps out at us and says, "Oh, of course, that's why that one makes sense." Right? There are other ways, you can interpret general relativity in a bunch of different ways,
Mm.
and the one that Einstein started with, and the one that makes a lot of sense to many people, is this sort of idea that that it's almost like we live on these bendable rubber sheets. That's a,
Yes.
lots of details of that analogy are incorrect, and so we have to be
Yeah.
careful. But
But it makes a lot
but
of physical sense to
it
common
does.
people.
So right.
Yeah.
So
Yeah.
there's other ways of thinking about
Yeah.
Einstein's general relativity, making it look more like something like Maxwell's
Yeah.
electromagnetism, which which have the same mathematical content, but
Yeah.
kind of physically realize it in some way that feels different.
Yeah.
It isn't necessarily different underlying it, because if it has exactly the same predictions, are they really different? I'm not sure.
So
So
it's a sort of a Homo sapien intuition problem. I mean,
yeah,
300,000 years, we fought lions and tigers. Um, we know if we climb a tree, maybe we can avoid that tiger. Our intuitions are very much physical,
yeah.
and anytime you challenge that, I think we get lost. Yeah.
Yeah, I mean, I'm very uncomfortable with many aspects of the many worlds
Yeah.
hypothesis, but it does, but I can see why it's compelling. It is, I think, the it is my favorite term for it, which I definitely didn't come up with, but it's a good one. Is it's ontologically extravagant, right?
Yeah.
Because
It is. Yeah.
the
No human
universe
can imagine this. No human can
is
imagine
so
this. Yeah.
incomparably
Yeah.
more vast than we can imagine.
Yeah. Right.
Um, that all of the things that could happen really do happen. For some, I mean, it's a very specific definition of could, but
Yeah.
nonetheless, it's a pretty expansive definition of could. And
On
so,
on the other hand, we grew up thinking only solar system exists, and then only the Milky Way exists. Now we know
yeah,
it's it's a vast thing out there. So our intuitions always failed us. What we see is not true, and so I mean, we should be at this position to say, yeah, I mean, none of the things that we believed before are actually true, and hence anything is possible, right?
yeah, more things in heaven and earth, Horatio, as Shakespeare said in Hamlet, right? So yeah, the universe seems to always be more extravagant than we think it's going to end up being. So
Yeah,
I wouldn't put money against it. Um,
yeah,
But as you say, absent a way to actually test it, it's very difficult to be sure whether we should take it seriously.
yeah.
And it does have it is also the case that it does have, I think, what its skeptics, and at the very least I'm on the fence. So what its skeptics would
Mhm.
call kind of technical problems about how you
Yeah,
define. So it still is a probabilistic theory, just like we were talking about
yeah,
before. So how
yeah.
do you define these probabilities? How are they made real in a sense? Why do these numbers that get attached to the different
Mhm.
worlds, essentially, how do they
Yeah,
end up describing probabilities? And
yeah.
the people who are the real partisans of this theory think that they've solved that problem, or even that it's a non-problem.
Mhm. Yeah.
But I think some of us who are a little bit further from the center of it feel that it's not a really adequate solution.
Mhm.
Yeah. Now that's not to
It's
say there
a
isn't one, but
yeah.
there just hasn't been done yet.
If I understand this correctly, Andrew, it has some nice mathematical properties to it. So it solves, some of the complex issues around quantum mechanics. But then, since we don't know if it is true or not, I don't know if we should spend any time on it. I'm an engineer, so I'm just being practical. Yeah.
Well, I think, theoretical physicists spend a lot of time on things that we don't know are true, right? That's what it's sort of the job
Yeah.
description. So yeah, the question is how much time, right? So,
Yeah.
people have made the claim that certain esoteric theoretical, theories, string theory is one that gets called out a lot, that
Yeah.
there's just too much person power in the world being spent on it. Maybe that's true. I'm not sure. It,
Yeah.
for a while, it did seem like the best, this returns to things we were talking about before. It seemed
Yeah.
like the best way of marrying quantum mechanics and gravity and Einstein's theory of general relativity.
Yeah.
I think the idea that that it is the best or only way to do that, I think, isn't so favored anymore.
Yeah. Yeah.
That doesn't
It's
mean it's
mathematically elegant.
yes,
And so we are in a position right now that we have a lot of mysteries, and mathematics is the only tool that we have left with. Many of these experiments cannot be run. We don't have the energy to do them, so we cannot prove them one way or the other. So we are in sort of a fantasy land of mathematics, and there, string theory clearly fits. So I want to go into, I didn't know anything about this, Andrew, cubism. So you say
hmm
here the final interpretation that I will discuss in some detail, and in many ways, the one that I subscribe to when I'm not shutting up and calculating, is called cubism. So rather than postulate the continued existence of branches and worlds, cubism takes the mathematics of quantum mechanics seriously. So I don't know anything. I haven't even heard about this, Andrew. So first of all, sort of define cubism and how it fits with this issue that we have been discussing.
Sure. So first, let's for our listeners, let's
Yeah.
explain that cubism is spelled QBISM.
Yes.
Okay,
Yes.
that's important. So Q quantum, right? It's not cubism, although it is named on purpose to echo the early 20th century artistic
Yes.
movement of Picasso and Braque, but
Yeah.
it's also intended to be very to be very quantum mechanical. Um,
Yes.
and its genesis was QB originally, but I would say not so strongly now, stood
Yeah.
for quantum Bayesian. So
Okay.
the quantum mechanics we've been talking about, and Bayesian, it's a word we had that hasn't come up, but it's been implicit in a lot of the things we've been talking about so far.
Yeah.
So
Yeah.
Bayesianism is this idea that the kinds of probabilities that we've been talking about, what they describe, are
Yeah.
not states of the world, but states of our understanding of the world. So going back
Okay.
to the dice
Yeah.
that we talked about before, right? You
Yeah.
said, well, it's not. You said if it's not a loaded die, then it's going to go up. Come up 1 and 6. But it's not really a. It's also you also need to know about the dice, but also you need to know how you throw the die.
Yeah.
Um, even if it were a loaded die, if even if it were a die that all had the same number of dots on every single side, if I didn't
Yeah.
tell you what that number was, right? If I
Yes.
said, well, it's a false die, it has the same number. What do you think is going to come up when I roll the dice? You'd have to pick randomly between 1 and 6 because I didn't tell you which one it was, even though so it's a very different system, but it's the
Yeah.
same probabilities. So probabilities to a Bayesian are about your internal state of knowledge,
Yeah.
and for a cubist, quantum mechanical probabilities are about internal states of knowledge too. So
Okay.
those wave functions that I talked about, they're not about they're not so much about what the electron is doing, it's about what you know about the electron,
Mm.
right?
Okay.
Where you'd be willing, and I think the real strong cubists, and I'm not
Yeah.
sure I put myself all the way into this camp, people
Yes.
like Chris Fuchs, Rudiger Schack, Blake Stacey, John DeBroda, they would say that it's a gambling commitment, right? If you had,
Mm.
what
Okay.
would you be willing to bet about what energy level the atom will be in when you make the measurement, right?
Mm.
That's what a probability is, and
Yes.
fine. I mean, I'm not sure I'm much of a gambler, but I understand the idea, um,
Yeah.
and 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 as a description of what probabilities are, I think that makes a lot of sense. The
Mm.
puzzle for quantum mechanics, which they aim to solve, they don't just say this is a puzzle and throw up their hands, is
Yeah.
quantum mechanics still makes strong predictions and commitments about the way the world could be. Right?
Yeah.
Not everything is possible. Not all probability assignments are possible. And
Yeah.
also in practice, we find from doing the experiments that there's a set of rules that actually give us good probabilities to assign in certain situations.
They're
So
correlations. They're
hmm?
correlations.
Yes. So
They're
where do these?
correlations. So, yeah.
That's right. So
Yeah.
where why do quantum mechanics rules work, right?
Yeah.
If they're only statements about our brains, really, about the way we should use our brains
Yeah.
as agents in the world, why do those principles of quantum mechanics, why do the rules that Schrodinger first wrote down this equation, 100 more than 100 years ago, before he thought about probabilities in this way at all.
Mm.
Why do those rules work so well? And that is the mystery. So Cubism says we're going to take this Bayesian idea of probability very seriously, and we're going
Yeah.
to try to tease out what what the underlying rules could be, given that what probability means is about the things that the agent does in the world, not
There's
about
a
what
set
the
of
world is doing.
constraints that you need to work. I quite like this, Andrew. So I have to learn more about this. So there's a set of constraints that you're working within in some ways, right? Is that the
Mhm.
way to think about it or no?
Yeah, so that's right. So they
Yeah.
constrain the kinds of probabilities that make sense to
Yeah.
assign to things. Because again, in this
Yeah.
worldview, probabilities are not things that are out there in the world. They're things you assign based on what you know. So the more you know about that die and the way it's
Mm.
thrown, the better your
Yeah.
probability assignment will be. Right? That's how you game the system. Right? If you in you know
Yeah.
if you can do a little bit better than the 1 in 6, then or the 1 in 32 of a roulette wheel or something like that, then you could end
Yeah.
up making a lot of money off the house, right? And it's the
Yeah.
same in quantum
Unless you're a
mechanics. So
marketer. If you're a
yeah,
marketer, you can make a lot of money without any of those. We have all this tech people going around. So I want to touch on one other idea. So you say here an idea called superdeterminism stipulates that the details of Alice's and Bob's separate experiments are linked, despite Alice and Bob being too far apart. So this is sort of the Bell's experiment, isn't it?
right. It's a description of of the
Okay.
the idea of Bell is that you do two experiments, but you start with some system that used to be in one place, so you could set it up in a very specific way, and then you
Yeah.
take the two halves of the system to two different labs,
Yeah.
and you ask what the two systems will see. And imagine, I think an example I use in the book is, imagine that you know that there's a box with an apricot and a pear,
Yeah.
grapefruit, and but you shake the box up, and then
Yeah.
you give one of the pieces of fruit to Alice and another piece of fruit to Bob, but you don't tell them which one. And
Yeah.
you ask, and once Bob opens his box, let's say he finds the apricot, then you are 100% certain, and he's 100% certain that
Yeah.
Alice will find the pear, or whichever one he didn't find, whichever one I said, I've
Yeah.
lost track. Um, and that's not mysterious at all, right? Um, and
That's analogous to Einstein's left socks and right socks thing, right? Sort of similar
Yep.
concept.
Yes, that's
Yeah.
right. So if you have a
Mhm.
left socket, but the problem is that what Bell told us,
Yeah.
the more amazing thing in quantum mechanics is it's not that simple, because once you have your piece of
Now
fruit,
you
or
tell
the
me.
yes, well, this is why you always lose socks. Um, Once you have your piece of fruit,
Yeah.
in fact, it's not a piece of fruit that we talk about. It's really one of these electrons again. Once you
Yeah.
have this system, you can do measure. You don't only measure what it is. You can measure lots of things about it. And it turns out that the measurements you can do are not consistent with the idea that that before you do the measurement, it's totally determined by what happened when the box was together and split up, and then it's just Bob gets his apricot and Alice gets her pear, right?
Yeah.
It's a much more complicated system where you can measure more things about it, and the mathematics is such that it doesn't work out that
Mm.
those could be predetermined properties of the two systems,
Mm.
right? Because yes, it's exact if you had like enough pairs of socks, and so if you knew how many left socks that Alice got and how
Mm.
many right socks that Bob got, then you couldn't really make the right predictions. It wouldn't work out in the right way, probabilistically, over making many, many experimental realizations. And so the question is, can we make that make sense? Can we
Yeah.
understand that system, which some aspects of are perfectly sensible? That yes, if I know what
Mm.
happens in one half, I also can know what happens in the other half, even if they're far away.
Yeah.
But quantum mechanics is weird that because you can change the measurement you're going to do at the last minute, that
Mm.
in ways where it should have been the case that you couldn't make a prediction about Alice until Bob not only made his experiment, but also decided what experiment to do. So
Yeah.
it seems that Alice's result is dependent on more than just what happened before, and
Yeah.
we don't really understand that.
Yeah.
And
Yeah.
um, the cubist idea is not so much that it isn't a mystery,
Yeah.
but it's not. But the mysteries are different than what you thought. The mystery that Einstein wanted us to think was happening here was
Mhm.
that some information was being transmitted at faster than the speed of light
Right.
when as soon as Bob
That's not
opened
the
his
case.
box.
Yeah.
That doesn't the mystery is
Yeah.
why these, to use the word you used several times exactly
Yeah.
appropriately, correlations,
Yeah.
is why these correlations are set up and how they are maintained despite all the freedom that Bob
Yeah.
and Alice have to do their different experiments.
Right. So I want to finish up with your last chapter, the oldest light, you say here. You say, I'm a cosmologist. I study the history and evolution of the universe. These are subjects that humans have explored for as long as we have records of our thoughts. Um, so I think about, quantum mechanics, cosmology more generally, as an insult on Homo sapien intuition. We are not built to learn these things, and we sort of stumbled into it. And there is no reason to believe we can actually learn them because our brains are not really designed for them. And so all the mysteries that we are finding, in some sense, is sort of a mismatch of the hardware and the information coming into the hardware. Well, how do you react to that?
Well, I would say I would put it a bit differently. So
Yeah.
I think what happened was Newton came along. I mean, not only Newton, but Newton came along, and what he realized, and Galileo before him, and probably innumerable people whose names haven't been given to us through history,
Yeah.
realized that the same things that apply on Earth apply everywhere else. The same
Yeah.
principles, now we call them physics principles, but the same principles apply everywhere. And once you're willing to make that leap,
Yeah.
then the idea that these brains that were honed, as you say, kind of, to avoid getting eaten by tigers, and indeed to try to,
Yes.
hunt those tigers down and eat them. Um,
Yeah.
um, the idea that those strategies that might work on Earth also might work to understand things far
Mm.
outside the
That's
Earth.
interesting. Yeah. Yeah.
Maybe, I think so. So it does require, this idea that I talk about in the book, this idea of naturalism, that the world,
Yeah.
not just the Earth, but the universe is understandable, and that it's understandable in the same way we understand what's happening in our labs or
Yeah.
with our friends, um, can apply, on vastly larger scales. Now, that doesn't mean that our finite brains are, quite capable of all the leaps that are necessary, and
Right.
maybe there are giant conceptual problems in our outlook, but
Mm.
I think the idea that the universe has been expanding in some way from a hot and dense early state about
Mm.
14 billion years ago to until today, I think some version of that theory, that hypothesis, that idea
Mm.
is almost certainly true.
Okay.
Some
Yeah.
version of that. Are we necessarily right in all of our understanding of how that plays out and how it's put together?
Yeah.
Almost certainly not. Um, but I would be incredibly surprised if we were just wrong about it, right?
Mm.
Because it's there because we measure. How do we see how fast things are expanding away from us or expanding away
Yeah.
from everything else? Is we measure those same atoms that we talked about at the beginning. The
Mm.
same lines in hydrogen that enabled us to develop this theory.
Yeah.
Measuring those are exactly how we find out that things are moving away from us. So that
Yeah.
is straightforward, right? Now, there are other people have indeed tried to test this theory. Scientists are really good at,
Mm.
at coming up with alternative explanations, and
Yes.
we've tried, like, there was this old idea called tired light. Maybe light doesn't. So what happens is we measure the so-called redshift or Doppler shift of
Yeah.
of the light from distant objects, and that tells us how fast they're moving away from us. And
Right.
people came up with this idea called tired light, that maybe there's some, in some very small way, that it doesn't really apply on Earth, just because
Mm.
the distances are so small and the times are so small, that light loses energy just kind of spontaneously because it's, it gets tired over time.
Yeah, I can see
And
that. So the lambda CDM, which is sort of an established theory right now, seems very inelegant to me. Let me make a statement. You can object to it. Well, we don't know 95% of it. 5% we understand. And then we are going to speculate on the 95%. That seems, I mean, it's not going to fly in any sort of business context, but it seems to fly in physics. So what do you think about that?
I agree. We are not in a great place. It would be good to understand that, but the theory is, I mean, the observations are what they are, and the theory is what it
Yeah,
is. And it's not that we don't understand anything about that other 95%. It's that we only understand a little bit about that other 95%. So about
right.
25% of that other 95% ha we know that it attracts gravitationally in a fairly straightforward way. We know
Yeah,
that it doesn't interact with normal matter strongly enough that it makes a difference most of the
yeah,
time. Um, so we know that much. Um, the remaining 70-ish% is
yeah,
even weirder. It also doesn't interact in a normal way with the normal matter of the universe, but it has, instead of attracting in
yeah.
a simple gravitational force way, it actually has a self-repelling property. The
Yeah.
gravity pushes. Um, Now, this is something that is completely baked into Einstein's theory from the very
Mm.
beginning.
Oh wow. Okay.
Um,
Yeah.
so it wasn't a revelation that it was possible. It was a revelation that it was out there because
Mm.
it was thought to not apply to the universe that we actually lived in. But it was
Yeah.
enough of a going possibility that when I was a graduate student in the late 80s and early 90s, it was something that was in all the textbooks as a possibility. It was then
Mm.
said, but we think it's zero, but it was always put in the books. And so instead of being zero, it's zero point 0.7.
Yeah.
So now the problem with zero point 0.7 is that it's sort of the natural number that you might have expected wasn't
Yeah.
1. The natural number that you might have originally expected if you knew nothing else about it except kind of a vague description of it from your
Yeah.
theory is you might have expected it to be something like 1 followed by 120 zeros. Um, which is a number big enough that I don't have a good name for it, right? But it's trillions and trillions and
Yeah.
trillions and trillions. Um,
Yes.
so the back of the envelope calculation fails miserably. But on the
Yeah.
other hand, okay, we need to be humble, right? It was just a back of the envelope calculation involving no actual known physics. It was just, well, if I
Mm.
had to pick a number, it would be either 0 or 10 to the 122, but it probably wasn't going to be zero point 0.7. So it turns out it's zero point 0.7. So now we have to figure out where does that zero point 0.7 come from. We
Yeah.
have various ideas. So
Yeah.
this is not a case where we don't have ideas. It's
Yeah.
just, again, kind of like the way of working in quantum mechanics. It's that we don't have a way to pick amongst the good ideas. And obviously,
Yeah.
at least n minus one of them probably aren't actually good ideas. And
Yes.
maybe all of them aren't good ideas, but so far we have lots of ideas. We just don't know what the right one is.
Yeah. I don't know if I mentioned this to you on the email. We might have been in Hyde Park together
Yes,
in
you
the
did
early
mention that. Yes,
90s. Yeah. I wasn't learning anything interesting. You were.
I was indeed. Yeah.
So, so let's just finish this up. So, I mean, we talked about a lot of things. Physics is still, it appears, on the cusp. I mean, we have this, I mean, we didn't talk about this. We have this Hubble tension,
Hmm.
as I call it. I had a couple of Chicago professors on the podcast. Um, so the Hubble tension, I mean, I just finish up with this. I know that I have to let you go. Um, we make different measurements from microwave background radiation and Cepheids and so on, and we get different numbers. And H naught is basically about how fast the universe is expanding, and we get different numbers on that. So that's what's called the Hubble tension. Where are we on that right now?
Well, it is still a tension, that is for sure.
Okay.
So tension is kind of a term of art because we like to be a little bit nicer than saying disagreement or discrepancy. But basically, when groups using one technique to measure this number, indeed, it's called the Hubble constant, it describes the
Yeah.
current expansion rate of the universe. When when we use one technique, we get a number about 72 plus or minus a bit less than 1.
Yeah.
And when another group does it, a group that I will say I'm more closely aligned with, we get a number that's about 67 plus or minus a bit less than 1, maybe a little bit
It's
less
good.
than
It's good enough for government work, but you guys are
good enough.
very stringent.
Indeed. So
Yeah.
67 and 72 plus or minus 1 are pretty far apart. And indeed,
Yes.
it's those are both enough less than 1 that it's a pretty significant,
Yeah.
statistically significant, as people like to
Because the
say,
error bars
distance.
don't
They don't overlap,
overlap.
and
I
they
think
don't
that's
overlap by,
interesting.
they miss each other by kind of a factor of 5 or so.
Oh wow. Okay.
So basically there are two ways in which this could be solved.
Yeah.
So the first way, which I fear is the right way, is that um, it's our understanding of the measurement process that we've used, one or the
Yeah.
other or both sets
Yeah.
of teams. Now, it is absolutely the case that everyone is being incredibly careful and doing the best they can.
Yeah.
So, we do, if it's the case that it's a mistake like that, then it's a very subtle one, and
Yeah.
it's hard to imagine how it has escaped our understanding so far. But
Mm.
both sets of measurements are built up kind of from lots of other measurements and lots of other bits of understanding, especially the one, so you mentioned one of them is sort of more or less directly trying
Yeah.
to observe how fast things are moving away from us and how
Yeah.
far away they are. And that tells us the expansion rate of the universe. Now, the problem is that we don't know how far away anything is. The only thing, how do we measure the distance to something? Well, if we're nearby, we can send a light pulse back and forth and measure how long it takes, or we
Yeah.
can get a ruler. Once things get far enough away, we have to resort to other techniques. For
Mm.
relatively nearby things, we have what's called parallax, which uses the fact that it's the same reason why we with two eyes actually have depth perception, because our eyes are far apart or
Oh,
far
yeah.
enough apart that they
Yeah.
actually get slightly different pictures of the sky or of what's in front of us. Well, we can do that, and we can do that even better than just putting two telescopes on the Earth, because what we can do
Mm.
is we can basically wait 6 months for a telescope that's orbiting the Earth now and 6 months from now,
Things
and
turn
then
around. Yeah. Yeah.
they're like the diameter of the Earth's orbit apart from each other. And so we can
Yeah.
see
Yeah.
stars even throughout our galaxy this way. It's a great technique. Um,
Yeah.
and we use that to calibrate other things that are called standard candles, whose
Yeah.
brightness we think we know, and we use those in turn to calibrate even further standard candles.
Yeah.
Usually these things called supernovae, which are exploding stars, which, because we understand a lot of the physics of how they explode, it kind of makes sense that they should be more or less roughly the same brightness. But you have to
Okay.
be careful. Just more or less roughly is not the same. So, so, and the difficulties with this technique are you have to bootstrap your way up from this more or less geometrical measurement of the parallax at
Mm.
the beginning, all the way up to these not quite standard candles of these
Mm.
exploding stars, right? So there's
Yeah.
lots of places where you could imagine going wrong. That's not to
Yeah.
say that's what's happened, but you could imagine. And then
Mm.
on the other side, this measurement using this very, very old light from the early universe,
Yeah.
that we can go wrong because it's a very indirect measurement. You're not measuring anything expanding away from us. You're measuring distances, and you're measuring the sizes of things on the sky, and you're sort of using the fact that it's a coherent theory to put it together. And
As an
so,
engineer, Andrew, I have to say I prefer the latter method because it is sort of pure data.
mhm,
It's the errors are interpretation errors that we could potentially correct. The measurement errors, any sort of systematics that might be in there, it's very difficult to
yep.
pinpoint and correct, right? Yeah.
Exactly. So the hope, of course, though, is that both teams are right. That's what we want to be true. We want both teams to be right, and instead we want our theory to be wrong. That's the exciting prospect, right? We want, as I said, I think the idea of the
What's
big.
wrong with you guys? Don't you
Well,
want the theory that explains everything? No.
I want a theory to explain everything, but I want to know, but I want it to be right, or I want it to be closer to right than the other theories. So right now we have something that we can understand, which is this Hubble tension, and it's
Yeah.
much more exciting if the prospect is not just that we made some mistake in our data analysis. It's much more
Yeah.
interesting and exciting if there's something fun and new going on in our theory, right?
Yes. Yeah.
because if there's nothing fun and new, then I can still do the calculations for the old theory. I'm an old man by now, and but but we want something for my grad students to be working on in a few years' time, some new and exciting theory. And so that's what we hope is true. We hope that our theory is falling apart. My fear is that the theory is still okay, but that our observations are being misinterpreted. But maybe you can have me on again in a few years, and we'll know the answer.
It's you putting the blame on the engineers. These guys measure things, and sometimes they don't actually do it properly. Um,
So I'm
in
definitely
any
not. No, I'm
case,
definitely not blaming the engineers. I'm not just saying we've sort of measured the length of something in our experiment
yeah,
wrong. No, it's much more subtle. It's much more the scientists. It's
yeah,
it's not just. It's just that we're never only testing the Big Bang theory, right? We're also testing our
yeah,
theory of our scientific instrument, basically,
yeah, yeah,
right? And that can be a pretty high level thing that we have to impose,
yeah.
not just the engineering when you put it together, but really understanding it at a deep level as we're doing the analysis. And that's the place where we could imagine still going wrong.
I know it's late in London, so I should let you go. I mean, this was excellent, Andrew. Yeah, thanks so much for spending time with me.
Thanks, Gil. It's been a pleasure.